Hey everyone, and welcome. Today, we're going to talk about the language that science literally uses to describe, well, everything. We're talking about the tools that explain everything from the temperature outside to the very fabric of space-time. So let's jump right in.
So how do we actually do that? How do we take the world around us and translate it into the language of math? I mean, think about it. Sometimes all you need is one little number, right? But other times, a single number just isn't going to cut it. It doesn't tell you the whole story. So here's our game plan. We're going to start with the absolute basics, the scalar. Then we'll level up to vectors. And after that, we'll get into the really powerful stuff, tensors. And most importantly, we're going to see why any of this actually matters in the real world.
All right, first up, scalars. This is our foundation. It's the simplest, most fundamental building block we have for describing something with a number.
So what is a scalar? It's just a number. That's it. Seriously. It has what we call magnitude, which is really just a fancy way of saying how much or how big. But that's all it has. There's no sense of direction, super simple.
And the crazy thing is, you use scalars constantly without even thinking about it. When you check the weather and see 25 degrees Celsius, that's a scalar. You weigh a bag of flour, 5 kilograms, also a scalar. The speed of your car, the price of your coffee, yep, all scalars. They all answer how much, but they never answer which way.
And that question, right there, is exactly why we need to level up. To get that missing piece of the puzzle, we need to upgrade from a scalar to a vector. This is the big deal with vectors. They have both magnitude and direction, so they answer two questions for us: how much and which way. You could almost think of it like taking a simple scalar and just attaching an arrow to it to tell you where it's pointed.
This comparison really makes it click. Look at your car's speedometer. It shows your speed, 100 kilometers per hour. That's a scalar. Now, imagine your GPS screen. It shows your velocity, 100 kilometers per hour north. That's the vector. It's the critical difference between just moving around and actually moving towards a specific destination.
And trust me, vectors are everywhere in the physical world. Gravity isn't just some random force. It's a force pulling you straight down. When you throw a ball, it has a velocity, a certain speed, and a specific direction. The wind is blowing from the southwest. You literally couldn't navigate a plane or predict a storm without them.
Okay, so we've got scalars for how much, and vectors for how much and which way. But what happens when things get even messier? What if you've got forces and pressures acting in all sorts of directions at the same time? Well, for that, we have to go even bigger. We have to talk about tensors.
Now I know, the word tensor can sound a little intimidating, but stick with me here. At its heart, a tensor is just a way to organize a ton of information about a system where things are happening in many directions at once. It's a generalization of the ideas we've already covered.
In fact, you already know the first two types of tensors. A scalar is actually a rank 0 tensor, just a single point of data. And a vector? That's a rank 1 tensor, a simple list of numbers. A rank 2 tensor, which you've probably seen before as a matrix or a group